So in the last video, we just talked about how to do a chi-squared test of independence. All right, and now we're going to look at a chi-squared test of homogeneity. Okay, and so what makes them a little bit different is the questions that is actually being asked of them. But besides that, everything else is the same. So let's just kind of review a little bit of the difference down here. So a chi-squared test of homogeneity means you're going to look to see, remember homo means the same, and so we're going to look to see if we have many populations here, is one characteristic among them the same, okay, or one variable. So what happens is we're going to take multiple samples from each population. So I'm going to have multiple populations, and we're going to look at a single variable within each of these different populations. And of course, that is going to be broken down into some sort of categories. Chi-squared enables us to use categories for categorical data. So go ahead and look down here at this question. These are some nice framing questions. It says, do North Americans and South Americans have a different distribution of wealth? And so when I am looking at that, I have multiple populations, North Americans and South Americans, and I'm going to be looking at the distribution of wealth, which could be broken down, that's my variable, into categories. Wealthy, not wealthy, of that nature. And here's another one. Do stats teachers and calc teachers have the same grade distributions? Okay, well again, here's one population of stats teachers, here's another population of calc teachers, and we are going to look at just one variable, which is the grade distribution, and that it can be broken down into categories such as, A's, B's, C's, etc. Okay, and so let's go ahead and look at some of our conditions that go into them. For this one, if we look at our null versus our alternative here, the null hypothesis for a test of homogeneity is that the population distributions are the same. One population is the same as the other, and the alternative would be that the population distributions are all not the same, or not all the same. Our degrees of freedom, still the same thing, because we'll have a two-way table. That's how we're going to calculate it. Our conditions are a little bit different. We add this back in here because now we're going to be having, not only do we need to check for randomness, not only do we need to check for independent selections, but we're going to have to check for independent groups. Like, is one of our populations different from another? And hopefully they are. Like, if we go back to the high schools, like Northern High School is different than Huntingtown High School. But you may have two populations. Like, you might say the populations of students who play, sports or who are in the play. Well, those two things or in the spring musical, those could overlap, right? Because I could play field hockey in the fall, but also be in the spring musical during the spring. So those aren't independent. So you need to make sure that these two things are actually independent of each other. All right, and again, expected values, you're going to do your row times your column, and it'll give you your table. To be honest, I just found major cheat code for that as well, although you totally need to be able to do that. I just showed you in the last video how to do that. I really kind of explored this for a second, and it's actually pretty cool. So in order to save a ton of time, if you use your matrices or your matrix and you type in your values and you do exactly what this tells you, your calculator freaking does everything for you. You do not need to enter the expected matrix. It does it for you, and I just did it last time, so that was a waste of time. But it's good because now you know how to find a single expected count, which is what you would need to be able to do. So let's kind of explore and check out this problem. So here is an example. Let's see it in its glory. It says 4 simple random samples were conducted on different ethnic groups of females who drank alcohol during pregnancy. Each respondent was asked the average number of drinks they consumed per week. Is there evidence that the groups of women have different drinking tendencies? Okay, so first off, we have to realize, and I feel like the screen's really dark or something, but first off, we have to realize that we're looking at 4 different, ethnic groups. There's 4 different populations, and they're lined up on the side for us. And then we're looking at one variable about them of how many drinks did they consume per week. And so because there's multiple populations, that's a huge sign that we have a chi-square test of homogeneity. Okay, among the different groups. So we're doing a chi-square test of homogeneity among ethnic groups with respect to their drinking habits. Okay, and so we said that our null hypothesis would be that the ethnic groups are, have the same distribution. So I would say the ethnic groups all have the same distribution of drinking habits. And the alternative hypothesis would be that the ethnic groups do not all have the same. The ethnic groups do not all have the same, and I mean, you could say distribution of drinking habits, but I'm good. Okay, so significance level here, you would want to say, you get to pick, but I'm just going to pick 5% again. And to check our conditions, you would have to check to make sure that you use random samples, which we did, independent samples. Oh, it's kind of sitting down here. Independent samples. We have different ones from different populations, right? They can't really, I mean, I guess you could have mixed, but we're not. They're different groups, right? And then if you're doing independent selections, normally we check for one population, but since you have 4 different ones, you would have to look at it for the 4 different ones. And we're going to assume that all of our populations are large enough for independent selections. And then for our large samples, we actually have to calculate all of our expected values. So this is where things got crazy, okay? So this is actually so cool. So if you follow along in the bottom of your notes here, because I kind of skimmed over this the first time, you can enter all of your data in a matrix and then do this test, and it'll give you all of the information, but it'll also give you your expected matrix. So I'm going to show you this new and fancy calculator, so lovely. Okay, so first thing you're going to do is hit the second button. So get out your calculator right now, pause it and get it out. Second, and then you look for the matrix button. That is right here. You want to click on just, actually you want to go over to edit. So click over to edit and just edit the first matrix that pops up. So you get to change, this is the number of rows and this is the number of columns. So on this one I want to have 4 rows, so I change it to 4. And the number of columns I want 3 columns, so I don't have to change that. It automatically populates zeros across the board. So you get to go in here and edit these. There you go. Just press down a couple times. And you just want to type in all the stuff that it has. And if you hit enter, it automatically scoots you over to the next one. It's very quick and easy just to jot all of these in here, like so. To be honest, this made me so happy when I found this out. Okay, so now that you have your matrix filled out, that's great. Okay, cool. If you follow along, you want to go to stat, test, and we want to go down to a chi-squared. Okay, we don't want to use goodness of fit because we're in a test of homogeneity, so we're going to pick the other one. Same with a test of independence, you pick this one as well, which I didn't realize, and if you look, it automatically populates your observed in number 1 and expected in matrix 2. Although I don't really remember doing anything for matrix 2, but the thing is it automatically does it for you, which is so freaking nice. So just scroll down and don't touch anything and hit calculate. And it actually comes up with you, like right now if you wanted to, it comes up with your p-value, your degrees of freedom, like your freaking test statistic, it's all there. I mean, there's no need to say the word freaking there, so I'm sorry. So I would put this in here as well, 14.1489. I mean, that's what you're going to go solve later, and you actually already have the answer. You already have the p-value, which is awesome. We're kind of working backwards with our steps, but remember, our calculator is so awesome, but we have to prove that we're awesome by showing our work. Okay, so yeah, and honestly, maybe write down your degrees of freedom over here on the side. Or we're gonna need a curve, so I guess we can just. Oh my gosh! I was about to draw a normal curve. Craziness. Remember, this is a chi-squared one, so it needs to be skewed. That doesn't even look skewed. Or obviously it's a little skewed, but I'm gonna make it dramatic. It's like a slanted mountain. I wish I was hiking. Okay, so degrees of freedom, we got, holy cow, this is a chi-squared test with 6 degrees of freedom. Okay, whew, sorry, let's work backwards. Okay, so the cool part now is, when you were starting this problem, you technically, and even in the conditions, you have to figure out what your expected values are. Technically, I didn't need to go fill out any of this, because we're going to do that all in a little bit. But now the cool part is, if you go back to your matrices, so if you click second, hit the matrix button, and you go down here and you click edit, and you look at matrix B, oh my gosh, they literally just calculated all of your values for you. So you don't have to go and do, because before, what you would have to do is you would have to like calculate all of these margins, and you would have to remember you would take this margin times this margin and divide it by the total to get best expected value, which you still have to know how to do. But for right now, we can kind of just cheat code this and write down all of the values that we have. So that is stinking awesome. So I would say you don't need to go that many decimal places out. Just go like 1 decimal, because otherwise it's not going to fit. So we'll do 72.4. I'm so happy. This 0.4, 108.6, 289.6. Like, wasn't that amazing, or what? It's the small things in life, guys. If you can't appreciate this, I don't know what to tell you. And not even added some math. Think of something that you're grateful for today, and realize that somebody else might not have something as good as you to be thankful about. Your life's pretty good. Okay. Besides getting your stats lesson, you're getting a life lesson with Benjamin here. Okay, so this took me longer than I thought. Okay, well, imagine calculating all those by hand. That would have taken forever. But we've just saved time, so it's good. So now that we have all of these, if we go back to our conditions, which was our large sample, we have to make sure that all of these are greater than or equal to 5. Holy cow, this one's pretty close to not being, but it is, so we're good. So I would say all expected values are greater than or equal to 5, so we're in the clear. Then we get to come down here and start actually finding our test statistic, or proving that we can get here. So remember, to prove this, we would have to take our observed. So our observed was 7. Oh, that's not even the observed. This is the observed. Okay. So we would take 80 minus our expected, 72.4, square that and divide it by 72.4. We would also do 12 minus 18.2 squared. I'm doing this 12, matches with this part, over 18.2 squared. Oh my gosh. You can do a plus, the dot, 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 and just do the very last one. The very last one would be 40 minus this one over here, 37.7 squared divided by 37.7. Okay, we've proved our worthiness. We know how to use the formula. Yay, we can just use the answer that they already got for us, and it's good to go. Literally already found the p-value. Come back over to your curve and make sure you make it beautiful. I mean, starts at 0. You just found your chi-squared test statistic. You got to put that on your curve, shade it, and you go and find the area to be. We already found it from the calculator. Calculator's our best friend. Okay, we got it all, and luckily this sheet, for whatever reason, this note section, literally has a nice thing on the bottom, so we don't have to write out our entire conclusion, and there's room. So I would say that the p-value of 2.11% is not smaller, is, oh wait, it is smaller than 5%, okay, is smaller than 5% significance. This result is significant, so I will reject the null. There is enough evidence to say, and then we have to look back up here at the alternative. The alternative was that the ethnic groups do not all have the same, and then this is where I got chintzy before. If you look up here, like I just ended with the same, but the same, I would come back up here and say distribution of drinking habits. Yay! Okay, you finished an example.